So we'll be discussing about bracketing method now. Okay. So what do you mean by bracketing method? I'm not going to say anything about what is a bracketing method, but I'll first talk about the very first method, that is bisection method, and then I'll come back to explain why this method has got this name of bracketing method. So we'll discuss about bisection method. Bisection method is also known as interval moving method or binary chopping method. These are the same name, another name for bisection method. Okay. So let us talk about the idea behind bisection method. So I'll talk about bisection method with the graphical analogy. Okay. So let us say that this is my x-axis, y-axis, and I have a function. Let me use different colors so that it's not too confusing for you guys. So I'll use this method. This is function fx. So it's looking like a straight line. It should not be a straight line, just should be a function like this. So I'm using different colors so that it's easy for you to understand. Anyways, so please bear with me. So let us come back to this. So what is the root here? So this is nothing but the root of a function. Okay. So what actually we do in bisection method? We first define two things. Okay, the lower limit and the upper limit. So what we do here is we define something known as the lower limit and we define something known as the upper limit. Okay, and this is going to be the value of fxl. Okay, this is going to be the value of fxu. Okay, so obviously this is going to be negative and this is going to be positive. So before moving further, how do we know that the root exists between 2 points? Can you guys answer this question? How do we know root exists between 2 points or interval? Okay, so how can we say that yes, that the root exists between these 2 points? So understand one thing. Here I have taken 1 point lower limit and here upper limit, and if you see the value of the function here is negative and the value of function is positive. So whenever the product of this function, whenever it is negative, that means the root exists. So this is the, what you can say, a method of checking whether the root exists or not. So this is very important. So obviously if you can see here, this was negative and this is positive. Okay. When the product of this is negative, so minus into plus comes out to be minus. When that is negative, that means definitely the root exists between these 2 points. Okay, so suppose if this xu instead of being here was here, can you say does the root exist? Okay, no, obviously it's not going to exist, because in this case what is going to happen, your XL is going to be negative, and also your XU is going to be negative, and the product comes out to be what? Greater than 0, positive, that is greater than 0. So obviously the root doesn't exist between these two intervals. So whenever you want to check whether the root exists between two intervals, what you have to do is you have to find out the value of function, and then you have to take the product of that function. And if it turns out to be negative, that means the root exists. Turns out to be positive, root doesn't exist. Okay. So this was about how we can check whether the root exists or not. Okay. So then what is bisection method? So what we do in bisection method is we take XL, we take XR, XU, and we define one more variable XR. What we do is we take the average of XL and XU, okay, and we define XR. So suppose the XR is at this particular point. So this is my XR. So this is going to be FXR. So what I'm going to do next is I'm going to find out the product of XL. I'm going to find out the product of XR. If that turns out to be negative, so now what I'm going to do is this will be my new XU. Okay, I'll remove that, will become my new XU. So that will become my, this will become my new XU. Then I can erase this. So now this becomes what? XU, and this also becomes X. Yeah. Now what I'll do is, now this was the first iteration. For the second iteration, again what I'm going to do is I'm going to take XL and I'm going to take XU, I'm going to divide, and I'm going to find out XR. So suppose my XR now, let me erase this now, this becomes XU, so this becomes XU. So now let us say my XR comes at this point. Okay, and this is going to be my FXR. So again, if you see my FXL into FXR, it turns out to be what? It turns out to be positive in this particular situation, because this is negative and this is negative. Negative becomes positive. Okay. If that happens, this XR now becomes what? Use a different color pen. This XR now becomes what? The new XL. Okay. This XR now becomes what? It was previously XR. Now it becomes new XL. Okay. So are you understanding? What we are doing is we are bisecting. We are as the iteration goes on, we are moving in this direction, and we are moving in this direction. We are moving close to our root. Okay. So as you perform this iteratively, you will move closer to your actual root. So this is known as your bisection method. Okay. That is why it has a name of interval halving. So what you do is you are just reducing the interval, also known as binary chopping. So you are chopping. Okay. So basically, if you imagine, what you are doing is you are chopping, and you are coming close to the real root. So this is actually bisection method. So why this is known as a bracketing method? So to solve this problem, we have to start with some XL and XU, that is lower limit and upper limit. Okay, and that is nothing but a bracket. So that is why this method is known as bracketing method. So again, in false position method also will require two endpoints. okay, so that we should be able to start solving the problem. Okay, so that is why these techniques is known as bracketing technique. So let us write down the algorithm. So what is the algorithm here? So this is bisection method. So XL will be given, XU will be given. What you are going to do is you are going to find out XR. And how you are going to find out XR? It's going to be XL plus XU divided by 2. Now, if XL into XR, the product of XL and XR is greater than 0, then your XL will be XR is going to replace your XL. That is, your XR will be your new XL. Okay. And if fx XR is less than 0, your XR will be your new XU. That means you are going to replace, for the second iteration, you are going to replace your XU by XL. And you are going to continue this till your approximate error is less than equal to your specified tolerance or specified error, also known as tolerance. Okay. So now at this point you might be thinking, what is this approximate error? Okay, so we have still not discussed what is approximate error, or else let me discuss it now. So now you know there are two types of metrics that you are going to use to find out whether your solution has converged or not converged. So one metric is your true error, true percentage error. Another metric is your approximate error. So when you talk about your true percentage error, what is the formula? It is analytical minus approximation divided by analytical. Okay. But the problem with the true percentage error is we'll not always know what is the analytical value. If we knew the analytical value, why the hell we are going to go for numerical techniques then? Okay. So in real life, you won't always know the analytical value. So that is why we generally don't use true error. We just use it in a very rare situation where we know the analytical value. And that is not going to be always possible in real life. Okay, so that is why we use this technique, this metric, that is approximate error. So what is the formula for approximate error? So approximate error is going to be your old approximate value minus your new approximate value divided by old approximate value. So whatever value you will be getting, that will be your new approximate value. Okay, and the previous value is going to be your old approximate value. So that is why you use approximate error, because we will not always know the real analytical value of the problem. Okay, so this is the algorithm for bisection method. If you understand this, you can also implement this in your MATLAB. It's very easy. Okay, you just have to follow this algorithm. Okay, now to understand this, how to solve this, let us take an example. Okay, so what we are going to do here is we are going to take a simple example here to understand how to solve this. So let us say the problem is this 0.5 x square plus 2.5 x plus 4.5. So what we have to do is we have to solve this problem first graphically, second using quadratic formula, that is the analytical method. Then we are going to use bisection method, okay, and then we are going to use false position method. We are going to use the same problem. So I'm not going to solve it graphically because it's very easy. What you have to do is just have to use MATLAB. You have to plot this graph on MATLAB, okay, and yeah, I mean just plot the MATLAB in MATLAB, and wherever it cuts the x-axis, that will be your roots. I think that it is going to cut twice, because when you talk about quadratic equation, you have two roots, okay, so it's going to cut the x-axis twice. Then you can use quadratic formula, okay, and then we are going to actually see how we are going to solve it using bisection method and false position. And don't worry, always in examination they'll provide you the value of xl and xu, that is lower limit and upper limit. So for bisection method, the lower limit and upper limit in this problem, let us say, is 5. Lower limit is 5 and upper limit is 10. Okay, don't worry, you don't have to assume this, it will be given to you in the problem. And we have to solve this bisection method till my approximate error is less than 2%. So I'll just keep on repeating, solving the problem till my approximate error reaches less than 2%. Okay. So let us start solving this problem. So graphically you can solve quadratic. Okay, I'll show the quadratic one. Quadratic formula. So we all know the formula for solving quadratic equation is this: root of b square minus 4ac divided by 2 into a. So when you compare it with this, you know, ax square plus bx plus c is the quadratic equation. So when you compare it with this, you'll realize your a comes out to be minus 0.5, b comes out to be 2.5, and c comes out to be 4.5. And when you substitute these values in this equation, the value of x1 is going to be 6.405 and x2 is minus 1.405. So let us so this is how you are going to solve it using quadratic equation. Now let us solve it using the bisection method. Okay, so bisection method, we are going to solve it. We will make a small table and we are going to solve it using the table. Okay. Now before I proceed, understand one thing, that bisection method is only going to give you one root. Okay, but since this is quadratic equation, you should have two roots, so it will only give you one root. And based on your initial lower limit and upper limit, I think this is the value, this is the root that we are actually chasing. Okay, this is the root that we are finding using bisection method. So for finding out this root, what you are going to do, you are going to use a different value of xl and xu, and again you are going to apply bisection method, and then you are going to find out that root. Okay, so bisection method is just going to give you one root. Understand one thing. So you have to apply it twice to be able to find the second root. Anyways, so looking at this algorithm, what we need the value of xl, xu, xr. Okay, and we don't need the value of fxl and fxr. We just need the magnitude, whether it is positive or just the sign, whether it is positive or negative, to decide. Okay, so I think let's make a table. So this is my method of making a table. Okay, this is what I feel that how should we solve. Even if you don't like to make table, you can solve it without making table as well. XR. Then I'll this is my percentage approximate error, percentage true error, and then this is going to be Excel fix R. Okay, so this is the what I feel should be my table based on my algorithm. So what is how I am going to start initially? So we know the value of XL and XR. The value of XL is 5. The value of XU is 10. Sorry, 10. Yes, did I say XR? Sorry, it's XU. So 5, 10. Now what you are going to do in the next step is you are going to find out the value of XR. You are going to use this formula, that is XL plus XU divided by 2. So when you do that, you'll find out the value of XR comes out to be 7.5. Okay. Now the question is how you're going to find out the approximate error. Okay. Now understand that the formula for approximate error is the old approximate value minus new approximate value. So in this case it should be XR old minus XR new upon XR old. But we don't have any value of XR old. Okay, so we'll have to wait for one iteration. Okay, so there won't be any value of approximate percentage error for the first iteration. Okay, and when you find out the true error, now how you are going to find out the true error? So this is the root we are chasing for. Okay, and what you are going to do is an analytical value, that is 6.405 minus the approximate value 7.5 divided by 6.405, and you'll realize that your true percentage error comes out to be 17%. Okay, I'm again reminding you, in real life we are not going to find out the true error because we will not know the analytical value beforehand. So basically we'll be doing approximate error. Okay, so let's move on to this. Now what you are going to do is we have to find out whether this product is greater than 0 or less than 0. Understand one thing, we don't want the value of FXL and FXR. We just want the magnitude. Okay, so if you substitute the value of XL, substitute the value of XL, that is 5, in this equation, that is here fx, you will find out that the value comes out to be positive. Okay, and when you talk about XR, when you substitute 7.5 in this equation, you will realize that the value comes out to be negative. So the product positive negative comes out to be what? Negative. Negative means it's less than 0. Okay, so whenever it is less than 0, what is going to happen? For the next iteration, your XR will become your XU. So for the next iteration, what is going to happen? This XR will become your XU. So this will become 7.5. And rest everything is going to be the same. When I say rest everything is going to be, I'm talking about XL. So I'll just copy down the value of XL. So again, what you're going to do is you're going to find out the value of XR. How you're going to find out the value of XR? So XR is going to be XL plus XU divided by 2. So again, 5 plus 7.5 divided by 2, that comes out to be 6.25. Okay, I think now you can find out the approximate error. Okay, old value. What is the value of EA? Old value 7.5 minus new value 6.25 divided by 7.5 into 100. Okay, just this. So if you do that, the value of approximate percentage error comes out to be 16.67%. And when you talk about the true error, it comes out to be 2.42. Okay, so understand, we have to stop when the percentage error, the approximate percentage error is less than 2%. Okay, so we have to it's 16.67, so we'll have to move for next iteration. Again, what you're going to do, we are going to substitute the value of XL and XR in your function, and we are going to find out whether it is positive or negative. So when you do that, you will realize that the value of XL is positive and the value of XR is also positive. So now in this situation, I think the product is greater than 0. So whenever the product is greater than 0, for the next iteration, your XR will become your XL. So what you're going to do for the next iteration? Okay, we have to do next iteration because the approximate error here is 16.67, but we want it to be less than 2%. Okay, so based on this, I think we'll go down. So what we are going to do, we are going to copy the value of XR in Excel, that is 6.25, and this will remain the same. And now we are going to find out the value of XR, that is XL plus XU divided by 2, which comes out to be 6.875. Okay. And now if you calculate the percentage error, it comes out to be 10%. And when you calculate the true percentage error, it comes out to be 7.338%. Again, when you put the values of XL and XR in your F function and see the sign, you'll see that this is going to be positive, this is going to be negative, and the product comes out to be negative. Okay, so whenever it is negative, again your XR will become your XU, so this is going to be 6.875. We are not going to stop here because this is still 10%. We want it to be less than 2%. So again, this is going to be 6.875. This is going to be, again we are going to copy 6.25. Again, add these two divided by 2. This comes out to be 6.5625. And again, the percentage comes out to be 54%. And this is 2.45%. Okay, again, it is not less than 2%. So again, you'll have to go for another iteration. Again, what you're going to check whether it is going to be positive or negative. So you'll realize that this is positive and this is negative. Again, the error comes out to be. So this is how you are going to do it. And again, according to the algorithm, where it is less than 0, your XU will become your XR will become your XU. So your XR will become your XU. 6.5. Okay. So you just have to do the same thing for next iteration. I'll just write down the values that I am getting. Okay. So now we'll stop here because if you see that the approximate percentage error is less than 2%. Okay. And so what is the value of the root that we are getting? So the value of root is 6.328. Okay. So this is how you are going to do your false position, your bisection method. Okay. Now what I do is I suggest you guys to follow the same method. This time take the value of XL as minus 4 and XU as minus 0.5 and find out the root, that is the second root. So this is your bisection.